Hi everyone, in this video I'll be doing Advent of Code 2021, Day 18. I'll be doing the puzzles and then explaining them afterwards. As usual, the code is in the GitHub repository, which is linked to in the description. And without further ado, let's get started with the puzzles. Alright, let's explain the puzzles. Today was the hardest it's been so far, definitely for me, because it took me quite a while and lots of complicated debugging. But anyway, let's talk about the puzzle. So we meet some snailfish in the ocean, and we need to help them with their homework. The snailfish homework is a math homework, and it's about addition. So the weird thing is that snailfish numbers are different from regular numbers. They are represented as a bunch of nested pairs. And at the end of all those pairs are some numbers, but it's recursively nested within each other. So what we can first notice is that these pairs can be represented as binary trees. And hopefully you know what binary trees are. They're just trees that have two nodes at most per two children at most per node. So take this example, 1985. The binary tree representation of this would be a node here. It's an empty node. To the left we have 1 and 9. And then to the right we have 8 and 5. So I thought this was the most efficient way to represent the shellfish numbers, and that's how we're going to think about them for the rest of the problem. So we're also given how to reduce a shellfish number, and how to reduce a shellfish number is kind of complicated, but also it's kind of simple. So for every pair that is nested inside 4 pairs, the leftmost such pair explodes. So when we're saying nested inside 4 pairs, we mean something like this. That would be a total of 4 nestings. So, for example, this pair over here would be nested inside 4 times because we have to go down 1, 2, 3, 4 times to get to this pair. That's what they mean by nested 4 times. If it's nested inside 4 pairs, it explodes. Otherwise, if there are no such pairs that are nested 4 deep, then we look for numbers that are greater than 10. So I mean at least 10. So if we had a 12 over here, or 10, but we would do the 12 first because it's the leftmost, then we would explode it and cause it to go into 2 6s. And exploding just means decomposing into left and right. Sorry. And splitting an even number between each of those children, rounding down the left one if necessary. So that's what splitting is. And then I'm leaving exploding for later because exploding is a little bit complicated. If we have this pair, for example, that's going to explode. Basically what happens is the left node value jumps to the left. In this case, there's no node to jump to. And the right node value jumps to the right. So this 6 disappears and adds on to the rightmost node to become a 16 in this case. And then the original pair gets destroyed and replaced with a 0. So that's what exploding is, that's what splitting is. Hopefully you read through the puzzle and understand what this means, getting a feel for it. There are some great examples right here. And then we are told how to add 2 shellfish numbers. It's pretty simple. Given 2 trees, so again we're thinking of shellfish numbers as trees, we just need to add these 2 trees together by combining them with a node at the top. So given these 2 trees, for example, these are shellfish numbers. To add them together, we simply create a new node and then join them together like so to create a new tree. After doing this addition, we have to reduce the shellfish number. So after every addition, there needs to be a reduction. Shellfish addition is not commutative, so if we add a plus b, for instance, we need to put in parentheses. It's also not associative, so, or maybe it might be associative. Maybe that's something for mathematicians to figure out, but we're going to assume they're not associative nor commutative, so that just means we need to put brackets to describe which additions we are doing first. So given this list of shellfish numbers, we're just adding all of them together one by one. So we're doing this plus this, reducing it, and then adding on the next one, and then reducing it, and so on. So the task is to, given a list of shellfish numbers, to reduce all of them, to add all of them together, find the reduced product, and then compute its magnitude, which is defined in a weird sort of way. It's 3 times the magnitude of the left plus 2 times the magnitude of the right, and any regular numbers are just themselves their magnitude. So how did I do this problem? It's pretty straightforward if you read the puzzle and understand it. This part is a bit confusing, where we have to find any nested pair first to explode before doing any kind of splitting. So if any pair at all in the shellfish number is capable of exploding, we have to do that first, regardless of whether it comes left or right of a splitting number. So since I'm representing this as a binary tree, I'm creating a class to represent one of the nodes in the tree. Any intermediate nodes are going to be empty because they don't hold any numbers, and only the leaf nodes, the ones at the very end with no children, are going to hold a number inside them. Otherwise, they have a left and a right property or attribute that just points to their children. I also included a parents attribute to point to its parents, but this is probably unnecessary, and you can solve it with... There's alternatives to this, but I found this the most straightforward and simple way. Okay, so that's how we're doing our trees and our shellfish numbers. After that, we have a parsing method for just taking in a list and converting that into a tree. Because we are given our data in the form of lists, and hopefully in your language there's a way of evaluating these lists out to literal arrays. In Python they're called lists. And we just convert them into a tree using this method right here. By the way, as a reminder, this code is all in the GitHub repository, which you can check out in the description. So don't worry if you don't catch all this code right away. You can always review it later. After that, we just have this simple add method to put together two trees and then reduce them. Then we have this function for computing the magnitude, which is the definition. It's recursive. And then we have this giant function, which is the reduce function, and this is really the crux of the puzzle. So here's the very high level outline for how to reduce a shellfish number. First, we look for exploding pairs, and then there's some details in here that I will fill in. Then we look for numbers that can split if there are no exploding pairs within the tree. I'm using tree and shellfish number interchangeably. If none of those happen, then we're done because nothing else can happen. No more reduction steps can be done. And if something has happened, then obviously the tree has changed, so we want to reduce it further. Alright, now let's look at how exactly we do a pair explosion. We're going to do a depth first search through the tree. We want to go from left to right because the problem states that we want to find exploding pairs that are the leftmost at any time. So doing a depth first search in pre-order traversal, and pre-order just means that we visit a node, and then we visit its left subtree, and then we visit its right subtree. As opposed to in order, which would be left, middle, right, or post order, which would be left, right, middle. We're doing middle. Oh, sorry, no, wait. We are doing pre-order. No, yes, we are doing pre-order, and that gives us the necessary order to find exploding pairs left to right. So we do this depth first search through the tree, and I'm using a stack here to kind of copy that recursive structure. So we're just looping through the tree. Now we need to detect if there are any exploding pairs. So we're looking for pairs that have a depth greater than or equal to 4, and we keep track of the depth as we do our depth first search with this parameter here, keeping track of our depth. So if the depth is greater than or equal to 4, and we have a pair as opposed to an intermediate node. Actually, sorry, I mean if we have an intermediate node that has 2 number children, then we want to consider this as a explosion candidate. If this is true, then we want to explode. And I'll go into the details a little bit later. And okay, after we explode, this deletes and becomes 0, and we reset some of the children. Okay, now how does the detail of the explosion actually work? So this is a pretty important part of the solution. So consider we want to explode 4, 5. All right. We could find the leftmost nearest left and nearest right nodes through some kind of pre-order, post-order traversal stuff, but I'm doing it the naive way. I'm keeping track of which nodes are the parents of any given node. So we can do this a lot more simply. Suppose we want to explode this pair right over here, and assume its depth is great enough. We want to find the nearest node to its left, and to do that we go up the tree until we find a node that has a left child. That is exactly right here. So while it does not have a left child, or its left child is still the current node, then we want to keep moving up. Once we reach a node that has a left child, we can go down one step to the left, and then we descend our way to the right. If you look here at a bigger tree, so something that looks like this, and it has like lots of branches going down everywhere. Maybe I'll do a better diagram. So it looks something like this, perhaps, where this is the root, and there's a bunch of branches in between that I'm not going to draw. If you start at a node and you want to find this node over here, that's to its left, you want to go up the tree until you find a node where you can go left. So you immediately go left, and then you descend your way to the right until you get to that node. So in this way, using these while loops, we get to the closest leftmost node, left node. Yeah, these are these two loops right here. But we also want to be careful if we're on one of the edges. Then finding a node to its left is going to be impossible. So we're just going to work our way up the tree, get to the root, and not find any nodes to its left. In that case, we just don't want to do anything. Similarly, for finding the closest node to its right, it's just literally the opposite. Yeah, we work our way up until we find a node that has a right child that has not been visited before, and then we work our way to the right and back down to the left. So you can see those details in the code, again, posted in the description. After that, of course, we want to do the depth first search. We are putting our right child first and then our left child because we want to make sure the left child is considered first for pre-order. Now, returning back to our roadmap, if there are no exploding pairs, then we look for pairs that can split. So first of all, if a pair has exploded, then we are not done. We keep track of this variable to see if we have done something yet. And if we have done something, then we want to continue again and reduce, ignoring these last few steps. Ignoring 2 and 3. Okay, now we look for splits. We do basically the same thing. We do a depth first search, and then if we arrive at a leaf node, so that's that condition over here, then we want to split if the value in there is greater than or equal to 10. We create new left and right nodes with these values, which are just divide by 2 rounded down and divide by 2 rounded up. And yeah, keep track of parents and just create those children. So that's the process for splitting up. And if we have split something up, then of course we want to reduce again because the tree has been modified. So that's the reduce method at a kind of high level. Again, check out the details in the code. After that, we just literally add together all of the nodes, all of the numbers in the input one by one, using the add function that we wrote earlier, and at the end find its magnitude using the magnitude function that we wrote earlier. Again, here's just that code. Feel free to pause the video and look at it a little bit. Okay, now for part 2. It's a bit more complicated. We have to find 2 shellfish numbers that add together to the maximum possible magnitude. Now, what we have to be careful of here is we cannot use 2 trees more than once. Because if we take 2 trees A and B and we add them together, they're going to get modified. That internal structure is going to get all messed up, and we can't reuse them again because the numbers aren't going to get reset. So what we have to do is loop through all of the numbers, and again, addition of shellfish numbers is not commutative, so we have to consider both x plus y and y plus x, but we have to make the numbers distinct. That's a condition in here. I need 2 different shellfish numbers. So we want to make sure they're not the same. We convert the lists to a tree, a shellfish number, because I thought this was just the most efficient way to do it. Instead of writing a copy function, we just literally reparse the list into a completely new tree. And since Python has great garbage collection, we don't have to worry about allocating any extra memory or any of that. So we have these 2 new trees, just looping through all possible pairs, computing their magnitude to the previous best magnitude, and then just printing out the best magnitude. That is the sum of any 2 shellfish numbers. So, I've been saying shellfish, haven't I? It's actually snailfish. So, anyway, that's it for day 18 of Advent of Code 2021. I hope this explanation was helpful. Hopefully you learned a bit from this video if the puzzle was challenging, or you solved it and just want to know how I did it. So I want to thank you for watching, and I'll see you tomorrow for day 19.